is sufficient. Okay. All right, so let's get to it. I wanted to talk a bit more about subroutines and the parameter passing and all of that fun jazz. Um, and I'm actually going to start in C for a couple reasons. One, I'm going to show you how you can mix C and assembly together, but then two, um, this sort of illustrates why we'll have to do functions the way that we need to do them. Okay, so let me write a stupid function that does nothing special, and all it's going to do is add two numbers and then print that the sum of them is whatever. Okay, so kind of a stupid example. Now, two things. Previously, like let's say that I was going to write a function to do the addition. Now, I wouldn't need to do this for real, right? Because I could just do plus. But let's say that I was being silly and I wanted to do something like this, right? Then I would have to define that function up here, right? Something like this. Okay, good. What about if I didn't want to define the function up here? What about if I wanted to define it down after main? And then I wanted to say int C equals add A and B, and then printf percent, let's see, the sum of percent I and percent I is percent I, and then pass it A, B, and C. All right, so let's say I wanted to do something like that. So what's going to happen if I try and compile this? Yeah, okay, it gives me a warning. Okay, now it did actually compile. Okay, so a warning and error are not the same thing. So, but it gave me a warning because as the compiler was processing the code, it first came across this instance of the add function, and at that point that it's hit the add function, have we defined what the add function is? No. Okay, now it didn't fail, the compile didn't fail because of course I did define the add function, I just defined it later. So the definition at this point is implicit because I haven't said anything yet, and later in the code I did that. Okay, now thanks. I can get around this by kind of in the same way that I can declare the existence of a variable without setting its initial value. I can say, hey, compiler, don't worry, I have a function that's going to be called add, and it's going to add two things, and I'll define it later. Okay, so I don't have to put all of my functions up above main. I can actually put them down below main, and then just have a list up here at the top of the functions that I'm defining further on in the program. Okay, so think of this as being sort of like if I did something like I said something like int num. I declare the existence of the variable num, but I've never actually initialized a value for it. It's kind of like that, but with a function. Okay, so now if we compile it, we no longer get that error. Okay, so that's now. Is there any reason that you want to put your subroutines all down underneath main versus above main? I mean, does it really matter in some sense? No. I mean, maybe it makes more sense to have main up top because, well, it's the main thing. But that's more of a just how do you want to organize your stuff, right? Uh, okay. So, and let's just actually make sure that it works correctly. Yay. Okay. Sum of 2 and 3 is 5. Okay. So, if I were writing a really, really big program, right, then I might actually want to have this add function or maybe a whole bunch of other functions in a separate file. Wouldn't that be logical? Okay, so how do we do that? So if I take this and I cut it, and then I make a new file, and let me just call it add.c, and I put that inside, okay? And then I compile it, and this time I need to give it, I'm using two C files, so I need to give it a list of all of them that I'm using. Func2 is sort of where our main routine is, and then I've taken this add code and put it in add.c, and then okay, so what's the problem here? Okay, multiple definitions of add. So I have here the definition of the function add in this file. Oops, I never saved it here. I'm sorry, that's why. Okay, never mind. Okay, still works, right? Now, what I probably should do is I really should add a keyword before this implicit definition to say that this thing is sort of external. And I do that by just saying extern. Okay. Now, strictly speaking, it's not necessary in this instance, because how did I write the add function? It was in C also, right? But if I wanted to, let's say I wanted to replace and no longer have the C definition of how to add this stuff, but I want to write the add stuff in assembly, okay, then I need to tell the compiler, okay, this bit is not written in C, but rather in assembly, and just sort of slot it in when you need it. Okay, so does that kind of make sense? Yeah? Okay, so if I compile it again, oops, compile, right? Still functions, still works, and yeah, as usual. Okay, good. Okay, so what I want to do is, instead of having this add routine being written in C, let's actually write it in assembly as a true function, okay? And have it, of course, obey the calling convention that it should. Okay, right? Good? Okay, so let's define a new thing, and I'll call this one add.asm. Okay, so now we're in assembly, right? So we need our data section, we need our text section, and in this case, where is main going to be defined? In the C file, right? So I don't need a main here because you can only have one main, right? So what I'm writing here is a subroutine that by itself won't necessarily look like it does anything, okay? So I'm not going to put the print statement here and so on. All it will serve to do is to be called by the other main routine, which for right now we have written in C. Now, of course, there's no reason that we had to write it only in C. I just did that to kind of speed things up for the printing part. Okay, so what is my and actually, let me just call this add func. Since add is an assembly instruction, I probably shouldn't call my function the same thing. Okay, and in fact, let me rename this file to be add func, and then in the C program, let's have it call not add, but add func. Oh, and then I need to add func. Okay, now I've got it. Okay. So, what is the code for add func? Well, add func is a function. Okay, so it's in a sense, it's a program in and of itself. Okay, what does every true function need to have to start and finish? The STP LDP pair, okay, and also a ret. Okay, so the first instruction would be store pair x29 and x30 relative to the stack pointer, and we'll talk about the stack pointer business later. At the end, you need this. Okay, and yes, I realize that the 16s are not the same. One's inside the brackets, one's outside the brackets, one's negative, one's positive, and there's an exclamation mark on one of them. All of that is necessary, and I'll explain what it all means later. Okay, but for now, just remember this is that breadcrumb thing, okay, that we've talked. Okay, and then finally a red. Now, I'm not going to have the move W00 here because I only need that in my main routine to give the number 0 back to the operating system. Okay, so if I'm writing a function that obeys the calling convention, it takes in what kind of numbers or what kind of data? 2 integers. Where should I expect that those integers are located for the purposes of my routine here? Okay, so located in memory, who knows? But are they also located someplace else? They're going to be in, well, okay, so they're defined in the C file, right? But right at the instant when the C file calls my function, how does it pass the number, in this case, what, 2 and 3? How does it pass that to my function? They have to go where? In registers. Okay, and it's W0 and W1, not X0 and X1, only because I define them to be ints rather than long ints. Okay, so fine, right? But they've got to be in registers. Yes? Okay, which registers according to the calling convention? Well, how many numbers am I passing to this function? 2. So the first number should be in the first register, which is W0 in this case, and the next one in W1. Okay, so I know that when I get to this point, W0 has input A and W1 has input B. And it's the responsibility of whoever's calling this function to put the numbers in W0 and W1. Okay, this function just needs to expect that they're going to be there. And this is why we have to have this calling convention in the first place, so that we know, functions know where to put data to pass it to other functions. Okay, we or no? Okay, so what do we want our function here to do with those 2 numbers? Wants to add them. And what are we going to do with the result? Well, the result's got to go someplace. And if we're to obey the calling convention, where should it go? Register 0. Okay, that's the first return location. So in this case, my program is going to do nothing more than this. Okay, now let's be clear on the syntax here. What does add W0, W0, W1 mean? Add the numbers in registers 0 and 1 and put the result in register 0. Okay, I nailed a number you on the midterm with that question. Right? So what's the value when the subroutine starts? What's the value in W0 and W1? 2 is in W0, 3 is in W1. Okay? When this instruction executes, what's in W0? 5. It's 2 plus 3. What's in W1? Still 3. Okay, I haven't destroyed it. It's still there. Now, do I care about it anymore? Not technically. I mean, I do insofar as I want to do some printing, but we'll get to that in a second. Okay. Okay, so are we cool that all this thing is going to do is just add the two numbers, put the result back in the first register, in this case W0, and return back to the function or the program that called it, which in this case is our main routine. Okay? Yes.
Why wouldn't you want to put it in W3 though? Because if you're printing, W2 because if you're printing.
Okay, good question. So, so the question is, why not just like, I know that I'm going to be printing this later, right? And if I'm printing, how was I printing? Well, I had the number A plus B equals whatever, right? And so what's got to go into the registers to accomplish that? X0 needs to have the address of the format string. W1 has to have the first number. W2 has to have the second number. W3 would need to have the sum, right? Okay, so Kiani's point is valid. Why don't we just circumvent this and go ahead and just put it in W3 because we know it's got to be there here in a few steps. Okay. Does that make sense that would save us trouble or save us time maybe? It's going to save us time, but it's not going to save us trouble. Okay. And the reason is that would disobey the calling convention. Right? Thou shalt obey the calling convention. Okay, so and we're getting to get there here in a minute, so you preempted me a little bit. Because right now, do we really have to worry about that? No, because the main routine is written in C. C is going to take care of it, right? But if I rewrite the main routine in assembly, which we will do, then I do have to worry about that, okay? And so what we'll do instead is, no, the function will obey the calling convention, damn it. The answer will be in W0. We will pass it back to main in W0, and then for the purposes of printing it, where do we need to put it? W3, so I can just move it, right? But thou shalt obey the calling convention. And if you don't, then I'm going to go find like a bunch of nuns or something and hand them rulers and have them chase you down. Huh? Oh, the stick. Oh, it's around here somewhere. So, unless this is one of those, you don't see it. Yeah. Well, every now and then my students mutiny and steal it and hide it from me. Um, and yeah. So, anyway, it's around somewhere. It's okay. Okay. So, let's make sure that this works, but then also let's talk about how we actually get this to compile, right? Because I have to do things in two separate stages, right? Because I've got some C and some assembly. Uh, so we've got to do them sort of separately. Okay, so I need to assemble the assembly, right? And I need to compile. Okay, so let's assemble the assembly first. So AS, and what did I call this? Addfunc.asm, and I'm going to make addfunc.o the object file. Okay, now I've got addfunc.o and func2.c, which is where my main routine was. So I'm going to link them and compile the C part of it together. So I've got func2.c and addfunc.o, and I'm going to out this to func2, the program. Okay, and now I have, well, my executable. Okay, and let's make sure that it works. It did, in fact, work. Okay, so I've mixed C and assembly. This, by the way, can be really handy for testing a program or particularly a subroutine because you can use C as sort of a glue, and then that way you can sort of concentrate on the function itself rather than all the stuff involved with printing and whatnot later. Okay. And also what this would mean is, say, for example, you were trying to really, really tightly optimize one little part of your program that was in C, you could optimize that part by writing it in assembly and still have the rest of it in C. Okay, so good. Okay, so we've got that. Yes? All right, so let's take basically our function or our main routine, okay, and let's essentially rewrite this in assembly. Okay, and so let me call this, how about func2.asm? Okay, we have a data section, we have a text section, we have a global function which needs to be called main. Okay, and first off, what does main being a function need to have? The store pair, basically throw down a breadcrumb, and then at the end, pick up the breadcrumbs. Oops. And then, because this is our main routine, we need to put 0 in register 0 to return it to the operating system. Okay, so that's all the usual stuff. Now, notice we did not have line 13 in our subroutine. Okay, we only need the move W00 to return the number 0 to the operating system, basically to say our program terminated normally. Okay, the convention with Linux anyway is that programs return an exit status to the operating system just to tell the operating system, yeah, I terminated and I terminated correctly, as opposed to I terminated because of some crazy bug. Okay, all right, so we need to set up a call to our function. We also need to define the two values, 2 and 3, okay, so that we can use them. And I'm actually going to define them up here in the data section. Okay, and I'll define them in hex. So A and B here I've defined as words. Okay, now, word does not mean what you think it does. Like, when you hear the word word, what do you think? Word. Word. Yo. Okay, but what is a word? Yes, a conjunction of letters. Okay, but that's not what we call a conjunction of letters in programming. What do we call that? A string, or in assembly, I would have typed .asciz for for a null terminated ASCII string. Okay, so a word has a different meaning. In our case, a word is a 32-bit chunk of data. Okay, and a D word, for double word, is a 64-bit chunk of data. Okay, now here I'm just defining a chunk of data. So the fact that I'm treating this as an integer as opposed to a floating point number or something, I've technically not defined. It's just a chunk of data. And how I treat it as an integer, a floating point number, something else, right, depends on how I use it later. Okay, is that all right? All right, so it's just a 32-bit quantity, and I picked a 32-bit quantity because how did I set up my function? What was it accepting? 32-bit integers, okay? If I wanted to recode all of this at the end to make it 64-bit, then I would change all my W's to X's, okay? And then the word would be instead D word for double word, okay? Word, yo. Yes? We have to have some humor at 8 in the morning. Yeah. Okay, so got those two numbers, and now I could load them into registers just by picking them, okay, by loading an immediate, okay, and so let me actually just do that for right this instant, which would be I could move W0 needs to have the number 2, W1 needs to have the number 3, and then what am I going to call at this point to add them together? The add func, okay? Now, when add func finishes, so on line 16, when we get there, what's in register 0? 5. What's in register 1? 3 is still there, okay? But should we count on the fact that 3 is still there? No. We should not depend on it still being there. Okay, in our case, it will be because our function didn't ever use register 1. Okay, but some functions might, and so you cannot depend on registers 0 through 18, basically, as staying what they were before you called a function. They might, but don't count on it. Okay, so what should I do with these numbers 2 and 3? I need to stash them someplace because I want to print the number 2 and 3 later. Okay, so where can I stash them to keep them safe? Okay, I can use X19 and up. Okay, those are non-volatile registers. I could also store them in memory. Okay, just for the moment, let's just stash them into non-volatile registers. Okay, all right, so what I'm going to do is move W0 to W19, and I'm going to move W1 to W20. Okay, now when I say move here, what am I really doing? I'm really copying, okay? Yeah, so this is maybe a misnomer of the word move, right? Move makes you think that the source disappears, right? If I move that book from one place to the other, it's not as if there's still a book on that table and in my destination, right? But in the register stuff, that's exactly what happens, right? We're really copying that data. Okay, good. We? Okay, so yeah, I know, right? Some sweet free government money. Yeah, yeah. The loan cancellation thing went live. So anyway, okay. So when I come back from my function, oh, on the subject, well, what do I want to do right after I get back from the function? I want to print some stuff, right? Well, what have I failed to define yet? Yeah, I haven't made my format string, so let's go do that. Okay, and let me just call it my string. Okay, all right, so now I've got my string defined. And so if I want to call printf to print this, what do I need to pass printf? Well, what's got to be an x0? The address of the format string, okay? So I LDR x0 with the address of the format string. What's got to be in W1? The first number, okay? And where have I stashed that temporarily? 19. So I need to move W1, W19. So that'll take W19 and copy it back to W1. Okay. What do I need to do with the other number? Same thing. And what is going to be in, actually, what do I need to do here before I do this? I need to move W0 to W3. Or, sorry, this way. Okay, why do I need to do that before I do the LDRX0 command? Exactly. Okay, where is the sum of the two numbers? It's in W0, right? That's where the function put it because that's the calling convention. And so if I don't have line 20 before line 21, I will obliterate the sum. Yes. Um, because the add function needs to have them in W0 and W1 in order to obey the calling convention. Don't make me go get those nuns. Okay.
You say with this one.
Yeah, nuns with rulers. Yeah. Huh? Yeah, that too. And they hate left-handed people.
That's facts.
Yeah. Um,
Thing on my head.
yeah. So actually, there's a good episode of Family Guy where they go to Vegas and Peter's getting chased around by a bunch of nuns with rulers. It's really, yeah, hilarious. So he gets on a bus and like it's full of just nothing but them. Yeah. Okay. Anyway, so um, right, we could have done that. Right, we could have put the numbers in W19 and W20 and had our add function know that. Okay, but like, trust me, that's actually going to cause you more headache in the long run than if you obey the calling convention. Okay. Well, okay. So, like, can we really F the calling convention? Why not? Right? It'd be nice if we didn't have to deal with it, but why do we have to obey it? Well, yeah, because we're using functions that we didn't write, namely things like printf, scanf, and so on, right? Well, I can't use those things unless like, we can't have uh, we can't use functions that other people have written unless there's some sort of convention as to how you communicate between how functions communicate with each other. That's the calling convention. And so if we gave up the calling convention, then we'd not really be able to use printf and stuff. And trust me, it'll make your life a lot easier if you just obey it. Okay. Even though, yes, I will admit that doesn't mean that we have to use a couple of extra instructions to get data to and fro so that it's in the place where it belongs. Yes. Okay. Freely admit that. Okay. But what's the alternative? Utter confusion. Okay. And in particular, like, look, does it really matter for simple little programs like this? I mean, other than the print part, no, it doesn't really matter. But if I'm trying to write a freaking operating system or something, right, that's going to have hundreds of thousands of lines of code, well, then suddenly it's going to matter, right? Because no matter how many registers you have, eventually you run out of them. And I should say, by the way, too, this calling convention, right? Who made up this rule or this calling convention? Or mainly, what is this calling convention specific to? Because there's really two pieces to it. What processor architecture are we running on? 64-bit ARM. Okay, so that's called ARCH64. And what operating system are we using on top of it? Linux. Okay, so it's the combination of those two things. If I were using ARM32 with Linux, ARM32 only has 16 registers, not 32. Okay, and so much of the calling convention is going to be similar, but which registers are non-volatile? Well, there's only half as many to work with, so there's a different convention there, and you better know that. What about if I'm using, oh, for example, my favorite processor? Any guesses? That's a computer, not a processor. But yeah, what was the processor inside the C64? Four numbers. 6502. 6502. Okay. Um, it it only has three registers, and in some sense only one, depending on how you count. Huh? It well, okay, because the there are the three registers are called the accumulator, the X index register, and the Y index register. And the X and Y index register don't have the ability to do most arithmetic except for incrementing and decrementing, right? So Think about it when you set up a loop, or say you set up a double loop, right? A loop within a loop. Well, you need two counting variables, right? I and j, say. Well, that's what you use your x and y registers for. And then your a register is where all the arithmetic happens. It also means that that architecture is very memory dependent, because you can't add two numbers. One of them has to be in a register and the other one has to be in a memory address, which is kind of weird, but yeah. And if that sounds interesting, I've got a class next semester to advertise. Yeah, CS-371, the retro computing 8-bit 6502 era. And I've got good news for you. When is it? It's not at 8 a.m. Can you guess what time it is at? No, 1:10. I know, right? Like, you're grimacing as if that's worse than 8 a.m. Yes, it needs to be a Tuesday, Thursday, because it's just that stuff doesn't. This stuff doesn't work in 50 minutes, right? There's too lots of assembly programming for a 50-year-old computer. Lots of projects. I hadn't decided yet. Huh? What kind of resources? Well, so this is the good thing about it being a 50-year-old processor. There's a lot of resources, lots of books and stuff. Uh-huh. And manuals and data sheets and yeah. Huh? You don't want to, oh, well, it's not that bad. So, all right. Um, so yes, we've had to add a couple of extra instructions in order to obey the calling convention, but just shut up and do it. Okay. Now, what this does mean, though, is you have to think a little bit now that our programs are going to start to get more complex, as to making sure that you have data stashed where you think you have it stashed. Okay. And what are the two options in terms of places that you stash data? Memory or registers. Those are your only choices. Okay. And we'll continue with this program to modify it to use memory instead of registers, to stash the number 2 and 3. But we'll get there in a second. Okay, good. All right, so are we ready to actually test whether or not this works? Huh? Yeah, okay, I think we got it, right? We've got this stuff sets up the call for printf. This stuff sets up the call for addfunc, and then we've stashed the numbers 2 and 3 in non-volatile registers just so that they're still around for printing later, okay? All right, so let's make sure that this all works. So I need to assemble, in this case, func2.asm and addfunc.asm, and I'm going to output those to func2.o. And then I need to link it, okay, which is an operating system-y thing, func2.o, and I'm going to output this to func2. And then let's run it, and of course we end up getting the exact same thing, right? It worked. Okay, now let me actually go back and reassemble this, but I'm going to do it with the debugging flag. Okay, so that I can go and use GDB. Okay, good. So let me open up a full terminal so that we'll be able to see it. Okay, so what's the instruction I'm about to execute? This STP thing. I haven't actually executed it yet. but that's what's about to happen. And I'm going to step through this. Okay, so what's in W0 and W1 now? 2 and 3 respectively. And we can see, in fact, what's in all of the registers there, right? So I can see that the number 2 is where I said it was, and the number 3 is where it said it was. What's in 19 and 20? Yeah, just random stuff at this moment, but if I step through 2 more instructions, now what's in them? 2 and 3, the numbers I stashed, okay? And I'm about to branch to the function addfunc, okay? Okay, so, good so far? Yeah? All right, so the other thing I want to look at, okay, is this thing called the program counter, okay? And we'll talk a lot more about this, but essentially this is like we need to start talking about how this breadcrumb system works. Okay, so how does my function addfunc, how do I know where to return back to? Okay, well, I'll show you. All right, so I'm about to go into the addfunc. I'm about to execute branch to addfunc. Okay, all right. And so if I step one more time, I'm now in the addfunc function, and let's look at our registers. Okay, what is this register here? The program counter has what value in it? 400768. That's in hex, of course. That's a memory address. And that happens to be the memory address where the first instruction of the addfunc code is located in memory. Okay. Also, what's in the registers? Well, 2 and 3 are there. Okay. And they happen also to still be in X19 and X20. Okay, good. All right. But what is in X30? It's this number, okay, 740. Let's keep track of that number for in a moment, okay? All right, let me step through. Okay, so I'm about to do the addition, and what's in my registers now? 5 and 3, okay, good. So 5, the sum is there. What's in my program counter? Okay, another number, right? And how many instructions did I execute? 2, right? Because I had my STP and I executed the add instruction, okay? All right, so how many bytes does an instruction take to encode in this architecture? Or how many bits, either one? Every instruction on ARM, 64-bit, is 32 bits wide. Every single one, period. Okay, how many bytes is that? 4 bytes. Okay, so when it says here addfunc plus 8, what does that mean? 2 instructions past addfunc, right? The instruction I'm about to execute is 2 instructions down from the start of the program. Okay, and so it counts up in 4s because each instruction is 4 bytes long. Okay, is that cool? Now, this, by the way, if you'll permit a digression for a moment, is one thing that's different about the ARM instruction set versus the Intel instruction set. Okay, in Intel assembly, not every instruction is exactly the same length. Okay, what advantages do you think that you could have if not every instruction was the same length? There's disadvantages too, but what advantages can you think of? Yeah. Okay, yeah, and simple instructions don't require a whole bunch of encoding, right? So a really simple instruction to do something could be 8 bits, right? Just do it. For example, our ret instruction, like we don't really need 32 bits to encode that, okay? But ARM does, okay? So in the other reason that the Intel well, okay, let me back up. The other advantage is you can load 64-bit immediate values, no problem. You just say load immediate, and you just have your numbers, right? And just boop, boop, okay, come on, keep coming, and shove it into a register. Can't do that here. You can't load a 64-bit number in its entirety. You have to do it in kind of chunks, which we'll talk about later. Now, so the advantage is that you don't have to spend as much data encoding simple instructions. Okay, but the other thing, and this is why Intel Assembly is still like this, how old is the Intel architecture? Huh? Yeah, like 50 years basically, right? So when we talk about Intel, the Intel architecture, we talk about what architecture? What do we call it? Huh? Ancient. Well, we call it x86, right? Why do we call it x86? Well, because what was Intel's, well, it wasn't their first processor, but what was sort of the first processor that's of this line? The 8086, okay, from 1972 or whatever it was. Um, okay, so then after the 8086, what did they put out? The 186, and then the 286, and then the 386, and then the 486, and then guess what was next? The Pentium, okay, which some people called 586, right? And then there was Pentium 2 and Pentium Pro, which some people called 686, and we stopped counting at that point, fortunately. Okay, somebody tell NVIDIA that. Um, anyway, uh, so what processor is in my laptop? It's an x86, right? This one's old enough that I don't have an M1 Mac yet. Okay, yeah, I know it sucks to suck, but well, okay, I could get a new laptop, but then we'd have to raise all of your tuition by $5. Okay, yeah, so yeah, because that's the school's laptop, not mine. Um, okay, but point being, um, it's an Intel processor. That thing can still execute code written for the 8086 from 50 years ago. Okay. And that's one reason that the Intel architecture is such a train wreck of stuff because it's got 50 years worth of baggage with it. Okay. Because it has maintained backwards compatibility as sort of one of its key features. Okay. Now, eventually, you're going to hit a dead end with that. Okay, so ARM architecture, and it's not the only one that does this, is an example of what's called a RISC architecture, RISC, for reduced instruction set computer. Okay, and um, on a RISC machine, every instruction is the same length, and it means instruction decoding is a hell of a lot easier. Now, there are disadvantages. Okay, so one of the reasons that the Intel architecture, and for that matter, 6502, had variable length instruction encoding was because what was really expensive in the 1970s? Well, a lot of things were, but okay, in terms of a computer, what parts were really expensive? Memory was expensive, right? And so your machines had kilobytes of memory, not megabytes or whatever. And so anything you could do to save memory was a good thing because that was the expensivest part. Expensivest, I just made up that word. Okay, the most expensive part. And in fact, do you guys actually know what memory used to look like? Because that's actually how Intel got its start, was doing solid state memory before they started building processors. This is crazy. You used to actually weave memory with little iron rings and little copper wires into a grid, and it almost looked like a little tapestry. Okay, it was called core memory. I've got 64 bits of it in my office. Actually, no, it's at home. I need to bring it into the office to build it. So anyway, this stuff was incredibly expensive because it was very tedious to build. And nowadays, though, is memory expensive? No, gigabytes are a dime a dozen, basically, right? So, okay. Anyway, so that was my digression on the architecture. All right. So, but anyway, program counter. This thing increments basically to load the address in memory of the next instruction. Okay, and if I continue stepping, I'm about to execute this ret instruction, and what has happened or what's about to happen is that, okay, the value that's in X30 is going to replace the value that's in the program counter. So what's in X30, blah, 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 740, and what's in the program counter? 774. Okay, if I step one more time, what's in the program counter now? 740. Okay, so what's happened is, what was the second to last instruction of our subroutine? That was the LDP thing, right? Pick up a breadcrumb. So I picked up the breadcrumb, and then the return instruction says, okay, whatever's in X30, put it, overwrite the program counter, and that's where you're going to go for the next instruction to execute. So this fundamentally is how subroutine calls are working. Okay. X30, by the way, is called the link register. And when we do BL, that's branch with link. Okay. Okay. All right. So if I continue to step through the program, all right, load the strings address, move the data, call printf, it prints. Okay. And then I'm about to execute the ret instruction. Oops. Registers is what I meant. What's in my link register? Blah, 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 A8C. Okay, and that's basically going to take me back and return control of the operating system. Okay, because our program's finished. And, okay, process exit normally. Okay, so we're good. Okay, good? Okay, so let's sort of recap everything we've done today. Okay, the first is how do you have multiple C files if you want them as separate files? Okay, and if you're writing a really, really big program, then obviously that kind of organization is a good thing. Okay, but this means that we can also mix C and assembly, and we could have assembly call functions we wrote in C, or C call functions we wrote in assembly, or just jumble it all up. Or, which of course is what we're really going to do, is do it all in assembly from the get-go, because that's the point of this class, right? Okay, the last thing that I probably should do, we'll go ahead and do this now, is let's go to here, and let's change this to not use those registers, but rather use memory. Okay, all right, so what I'm going to change here is I'm going to remove these 4 instructions. I'm going to remove that instruction. I'm going to remove this instruction. I'll have to put some extra stuff in, okay? Because what needs to be in W0 to call my add func? The first number, whatever it is, okay? In this case, it's 2. All right, so what I'm going to do is I'm going to load a register, and for reasons that'll become clear in a moment, I'm going to load X2 with the address of A. And then I'm going to load W0 with the thing referenced by X2. Okay, so this is called an indirect load. Basically what I'm doing is I'm telling the processor, I want you to go out into the memory, and at location something, there's some data. Pull that 32 bits worth of data from memory into a register, okay? But what's the problem? Do I actually know the location of my first number in memory? It's there someplace, but I don't know the number right now, okay? And so what I'm going to do is take the location of it in memory and put that number in x2. And I have to put that one in x because its a memory address is 64 bits, okay? But then what I can do is say, okay, computer, I want you to go to register x2. Open that mailbox. There's a number inside. That number is the mailbox I want you to go get my package out of. Okay, does that make sense? Yeah. All right. Now, maybe some of you guys actually have done this before. Does anybody like? And I don't think this works this way in Sparks, but like, for example, in apartment complexes and maybe some housing subdivisions, how do you get a package if it comes in the mail? Okay. What happens if it's too big for your mailbox? There's a little slip, or so like for example, my parents where they live, they don't have mailboxes out front of all of the houses. I don't know why they didn't do this, but whatever. Instead, they have a like big units of mailboxes sort of dotted around the subdivision. Okay, so when my parents want to go check the mail, they have to go over to a box that's a, you know, 10 houses over or something. And there's a bunch of boxes there, okay, that are sort of normal size boxes, kind of like you guys have down in the basement of Sparks. Okay, so let's say that they get a package. My dad opens the mailbox, there's a bunch of letters, but then what does he find if there's a package that's too big to fit in his box? He finds a key with a number on it. And what does he do with that key with the number on it? There's another bigger box, okay, that he puts the key in and opens it, and there's his package, right? That's an indirect reference to a mailbox. He got the mailbox number out of his mailbox and then went to a different mailbox to get its contents. And that's exactly what I'm doing here. Yes? Okay. So if I can do this for the number A, what else should I do? Let's do it for the number B. Okay, now in this case, which register should I use here? I could use X3, but I'm actually just going to use X2. Okay, because once I've loaded this thing into memory, do I care about the value anymore? Nope, no longer care. Okay, so that will have the numbers where they need to go. All right, now, when I come back from my func, where is the answer? It's in W0. Where do I need it for printf? I need it in W3. All right, so let me move W0 to W3. All right, in order to call my addition, I need the strings address in X0. Okay, so we still got that. But I also want my two numbers in 1 and 2. Okay, so let me just pull the same gambit. But this time I need to use X4 because I don't want to overwrite what I just put in X3, right? I worked hard to get it there. All right, so I'll put this, and then I'll do load W1 with the address of that's in X4, and then I'll do X4 with B, and then I'll load W2 with the thing that's referenced by X4. Okay, good. All right, so let's assemble it and hope I didn't screw anything up and link it. And let's run it. And sure enough, it still works. Okay. Now, this relative addressing is key to doing processing of things, and we'll talk more about it later. Okay, yes, Patrick. The address of A, right? So, what's that like in C? What gives you the address of something in C as opposed to the thing itself? The ampersand, okay, right? So the star, when you use a star, you're saying, okay, this as a pointer to that thing. But if I've got an int, let's say it's just the int num, how do I get the address of it? I do ampersand num, right? The types of variables that store that are pointers, which when you declare them, they have a star, okay? All right, so is that good? All right, we're gonna quit the stream right here, but we're not done for the day. All right.